There is a conversation happening right now in the physics community that almost never makes it into the press releases. It happens in the corridors after conference sessions, in the emails that don't get forwarded, in the long pauses that follow certain questions during seminars, when someone raises their hand and asks something that everyone in the room has been privately thinking but nobody wants to say out loud. I have been in those corridors. I have sat in those seminars. I have watched brilliant people go very quiet when the question lands. The question, stripped of its technical scaffolding, is this: what if we are wrong? Not wrong in the ordinary way, that science is always provisionally wrong, always ready to update, always holding its conclusions loosely in anticipation of better data. Wrong in the deeper way. Wrong in the way that means the foundation we have been building on for 100 years has a crack in it that we have been papering over, a crack that has now gotten wide enough that the wallpaper is visibly buckling. I want to be precise about what I mean, because precision matters here more than it usually does. I am not talking about the kind of wrongness that gets corrected by a better experiment or a more careful calculation. I am talking about the kind of wrongness that preceded the Copernican revolution, the kind that preceded relativity, the kind that preceded quantum mechanics, the kind where the anomalies have been accumulating for long enough that the honest response is no longer to explain them away, but to sit with the uncomfortable possibility that they are trying to tell us something fundamental. And what they may be telling us is that the laws of physics, the equations we have tested with extraordinary precision, the framework that has survived every experimental challenge we have thrown at it for over a century, are not the final story. Not even close. Something is rewriting them. Something we have not identified. Something that is leaving fingerprints in our data that we have been trained, institutionally trained, to interpret as noise. I want to take you through what those fingerprints look like. I want to show you where the anomalies are, why they matter, and why the people who understand them best are the ones who are most reluctant to speak about what they might mean. Because the reluctance, I think, is itself one of the most interesting parts of the story. Let me start with something called the Hubble tension. The name sounds technical and dry, and I understand if your eyes want to glaze over at the sound of it, but I want you to stay with me here, because this particular anomaly is, in my estimation, one of the most significant unsolved problems in all of physics, and it is not getting the public attention it deserves. Here is the situation. The universe is expanding. We have known this since Edwin Hubble's observations in the 1920s, confirmed by countless independent measurements since. The rate of that expansion is described by a number called the Hubble constant, which tells you how fast a galaxy at a given distance is receding from us due to the expansion of space itself. Now, here is the problem. We have two completely independent ways of measuring this number. Two different methods using different instruments, different physics, different assumptions, different teams of scientists working in different institutions on different continents, and they give different answers. The first method looks at the early universe. We use the cosmic microwave background, the faint glow of radiation left over from 380,000 years after the Big Bang, the most precisely measured thing in the history of science. We fit our standard cosmological model to that data. We evolve it forward in time through 13.8 billion years of cosmic expansion, and we get a prediction for what the Hubble constant should be today. The answer is approximately 67.4 kilometers per second per megaparsec. That is a very specific number. The second method looks at the local universe. We measure the distances and recession velocities of nearby galaxies using what astronomers call the cosmic distance ladder, a chain of measurements that begins with variable stars called Cepheids and extends outward through supernovae and other distance indicators. This method, led by teams including the one that won the Nobel Prize for the original discovery of dark energy, gives a Hubble constant of approximately 73 kilometers per second per megaparsec. Now, you might look at those two numbers, 67.4 and 73, and think, well, that is a modest discrepancy. Measurements are imprecise. Maybe it is just experimental error. But here is where the story gets serious. Both measurements have been refined and checked and cross-validated for years. The statistical significance of the discrepancy has grown to the point where, by the conventions of physics, it is now well beyond what we would attribute to random chance. The probability that this disagreement is a statistical fluke is vanishingly small. Something is genuinely wrong. The question, the one that physicists are finding very hard to answer, is what? What could cause the universe to expand at one rate when measured against the early universe and a different rate when measured in the local universe? The standard cosmological model, the model we have built our entire understanding of cosmic history on, does not have room for this discrepancy. The model assumes that the physics governing expansion has been the same throughout cosmic history. If the two measurements are both right, and increasingly it looks like they are, then that assumption is false. I want to let that sit for a moment. The assumption that the physics governing the expansion of the universe has been consistent throughout cosmic time may be false. That is not a small statement. That is a statement with implications that branch in every direction across the whole of physics. One possibility is that dark energy, the mysterious stuff that is driving the accelerating expansion of the universe and that makes up about 68% of everything, is not a constant. We call it the cosmological constant, lambda, and we treat it as a fixed feature of the universe, an energy density of empty space that does not change. But what if it changes? What if dark energy evolves over cosmic time, growing stronger or weaker, responding to conditions we do not understand? If dark energy is dynamic rather than constant, the expansion history of the universe would be different from what our models predict, and the Hubble tension would start to make sense. But dynamic dark energy is not a small modification. It is not the kind of thing you can slip into the standard model without disturbing everything else. If dark energy evolves, it means the vacuum of space, the nothing from which everything emerges, has a physics we do not understand. It means that the quantum mechanical properties of empty space, which are already embarrassingly poorly understood, are more complex than we thought. It means that our deepest theories of how the universe works are missing a piece. And here is what makes me particularly uneasy about this. We do not have a good candidate for what that piece might be. Theorists have proposed dozens of modifications, quintessence fields, modifications to gravity, extra dimensions, early dark energy that was stronger in the first moments of the universe and then faded. Some of these proposals fit the Hubble tension data reasonably well. None of them fit everything. None of them have the clean, elegant, inevitable feeling of a true solution. They feel like patches, and patches are what you apply when you do not yet understand the underlying problem. But I want to go further, because the Hubble tension, serious as it is not the only anomaly. It is not even the strangest one. Let me tell you about something that has been quietly unsettling the community of physicists who work on the foundations of quantum mechanics. Something that has been building in the data for years and that connects in a way I find genuinely profound to the deepest questions about the nature of reality itself. You are probably familiar with quantum entanglement. Two particles interact and become correlated in such a way that measuring one instantly affects the state of the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, and spent years trying to show that it could be explained without invoking any genuine non-local connection between the particles. He believed deeply and with good physical intuition that the correlations were pre-programmed, that the particles had local hidden variables, predetermined answers to every possible measurement question, and that the apparent spookiness was just an artifact of our incomplete knowledge. In 1964, the physicist John Bell derived a mathematical inequality that could, in principle, distinguish between Einstein's local hidden variable picture and genuine quantum non-locality. If local hidden variables existed, Bell's inequality would be satisfied. If quantum mechanics was right about entanglement being genuinely non-local, Bell's inequality would be violated. And experiment after experiment for 60 years has violated Bell's inequality. Quantum non-locality is real. Einstein was wrong about that particular argument. But here is what I want to draw your attention to. The experiments that have tested Bell's inequalities have been getting progressively more careful, progressively more loophole-free, closing off every possible classical explanation for the correlations. And as those experiments have gotten more precise, something unexpected has been happening. The violations of Bell's inequality are coming in larger than quantum mechanics predicts. Not by a lot, not by enough to shout about in press releases, but systematically, persistently, stubbornly larger. This is a very strange thing. Quantum mechanics has been extraordinarily successful. Its predictions have been confirmed to a precision of better than 1 part in a billion in some systems. The theory is not the kind of theory that gets casually wrong. So when experiments consistently show violations of Bell's inequality that exceed the quantum mechanical prediction, you have to ask a serious question. Is the theory missing something? The conventional response has been that the excess is due to experimental imperfections, to sources of noise or systematic error that are not fully accounted for in the analysis. And that may be right. I want to be honest about that. Experimental physics is hard, and anomalies that look significant often dissolve when the experiment is done more carefully. But these anomalies have not dissolved. They have persisted across different experimental teams, different physical systems, different approaches. And the more careful the experiments get, the more the anomalies remain. What would it mean if quantum mechanics itself were incomplete? If the correlations between entangled particles were even more non-local than quantum theory allows, connected by some structure or mechanism that our current framework does not capture? It would mean that the theory we use to describe every atom, every molecule, every chemical reaction, every semiconductor, every laser, everything is a very good approximation to something deeper, something we have not found yet. And I find that possibility, I have to admit, both disturbing and thrilling in almost exactly equal measure. Disturbing because it would mean that the edifice of modern physics, built with such extraordinary care over a century, is less complete than we believed. Thrilling because it would mean there is something genuine still to discover at the very foundations. Now let me tell you about a third anomaly. This one comes from a completely different direction, from experiments not in space but here on Earth, in the most controlled laboratory environments ever created by human beings. For the last 20 years, the standard model of particle physics has been one of the most tested and confirmed theories in the history of science. It describes all the known particles, all the known forces except gravity, and their interactions with extraordinary precision. When theorists use the standard model to predict the outcome of an experiment, and experimentalists go and do the experiment, the agreement is typically extraordinary, sometimes to 10 decimal places. But there is a particle called the muon. The muon is like a heavy electron, about 207 times more massive, the same charge, the same quantum numbers, just heavier and unstable. And the muon has a property called its anomalous magnetic moment, which describes how it responds to a magnetic field. The standard model makes a very precise prediction for this quantity, and for years, a discrepancy between theory and experiment had been quietly accumulating. The experimental value was slightly larger than the theoretical prediction. In 2021, the muon G2 experiment at Fermilab announced its first results. The discrepancy was confirmed. The muon was behaving in a way that the standard model does not predict. The statistical significance was 4.2 sigma, meaning the probability of this being a random fluctuation was about 1 in 40,000. Not yet at the 5 sigma threshold that physics conventionally requires to call something a discovery, but well past the point of comfortable dismissal. And subsequent data from the same experiment has kept the discrepancy alive. What does it mean for the muon to behave differently than the standard model predicts? The standard model calculation for the muon's magnetic moment includes contributions from every known particle. The muon interacts briefly with virtual particles that pop in and out of existence, and each of those interactions contributes a tiny correction to the magnetic moment. If the experimental value is larger than the theoretical prediction, it means there are contributions being missed. There are particles or interactions that the standard model does not include. There is physics beyond the standard model that is affecting the muon in ways we have not accounted for. Physics beyond the standard model is not a casual phrase. The standard model is the most complete description of matter and forces that we have. Beyond it lies unknown territory. Candidates have been proposed: supersymmetric particles, dark photons, new gauge bosons, leptoquarks, but none has been directly detected. The Large Hadron Collider at CERN has searched for these particles with extraordinary sensitivity and found nothing definitively new. Whatever is affecting the muon is either very heavy, above the energy range the LHC can reach, or very weakly interacting below the sensitivity of current detectors, or genuinely something we have not yet imagined. That last possibility is the one that keeps theorists up at night. I want to pause here and take stock of what we have so far. 3 anomalies from 3 completely different areas of physics. The Hubble tension, which suggests that the expansion history of the universe does not match what our best cosmological model predicts. The excess violations of Bell's inequalities, which hint that quantum mechanics may be incomplete at the deepest level. And the muon anomaly, which suggests that the standard model of particle physics is missing particles or forces that are real and present in our universe right now. These anomalies could each be wrong. Each one could turn out, with better data or better calculations, to evaporate into noise. That has happened before in physics. Anomalies that seem significant have dissolved under closer scrutiny. I want to be honest about that possibility. Science requires that honesty. But here is the thing. All 3 anomalies exist simultaneously. They have persisted through years of attempts to explain them away. They come from completely different experimental domains and theoretical frameworks, and they are all pointing in the same general direction, toward the conclusion that the physics we have, magnificent and successful as it is not the whole story. And there is a 4th anomaly that I have been saving, because it is the one I find most personally arresting, most philosophically interesting, most difficult to simply fold into any existing framework. It comes from the field of cosmology, from the study of the very large-scale structure of the universe, and it has a name that is almost comically understated given its implications. It is called the S8 tension. S8 is a parameter that describes how clumpy matter is in the universe. How much structure there is, how concentrated galaxies and galaxy clusters are compared to a smooth distribution. Like the Hubble constant, it can be measured 2 ways. You can predict it from the cosmic microwave background using the standard cosmological model, and you can measure it directly from the large-scale distribution of galaxies we observe today. And like the Hubble constant, the 2 methods give different answers. The early universe prediction says matter should be more clumped than it appears to be. The universe we observe is smoother, more homogeneous at large scales than the standard model predicts it should be. Matter has not clustered as aggressively as the equations say it should have. And again, the discrepancy has grown over years of increasingly precise measurements. It is not going away. 2 tensions in 2 completely independent properties of the universe, both pointing in the same direction. The standard cosmological model, lambda CDM, is predicting a universe that is expanding faster and more clumped than the one we actually live in. That is a statement about the model being wrong in a fundamental way, not in the details, in the foundations. What could cause both of these tensions simultaneously? This is where theoretical physics is currently working very hard with very few agreed upon answers. Some proposals involve modifications to dark matter. Perhaps dark matter is not completely cold and collisionless, as we assume. Perhaps it has weak self-interactions that affect how it clusters. Other proposals involve modifications to dark energy. Perhaps it evolves over time in a way that affects both the expansion rate and the growth of structure. Some proposals involve modifications to gravity itself, to the equations of general relativity, which we have tested extremely well in the solar system and in binary pulsars, but never at cosmological scales. And some proposals, the ones that tend not to get made at conferences, but that get quietly discussed over coffee, involve something more radical. The possibility that the standard cosmological model is missing something conceptual, not just a new particle or a modified equation, but a new ingredient that changes the picture at a fundamental level. Let me tell you what I mean by that, because I think it is important. The standard cosmological model treats space as a smooth, continuous medium. It treats dark matter as a cold fluid. It treats dark energy as a constant. These are approximations, and like all approximations, they are valid in some regime and break down in others. We do not know where the regime of validity ends. We have assumed, somewhat optimistically, that it extends to the scales we observe, but the tensions suggest it may not. If space is not a smooth, continuous medium at all scales, if it has a granular structure at the Planck scale, the smallest length scale at which general relativity can be trusted, then the equations governing cosmic expansion and structure formation might have corrections that become significant on cosmological scales. Quantum gravity, the theory that reconciles general relativity with quantum mechanics and that we do not yet have, might leave fingerprints in the large-scale structure of the universe. Fingerprints that look from the outside exactly like the tensions we are measuring. This is speculative. I want to be clear about that. We do not have a complete theory of quantum gravity, and without one, we cannot make precise predictions about what its fingerprints would look like. But the direction of the speculation is motivated by real data and real theoretical pressure. It is not idle fantasy. Now I want to take you somewhere that the conversation rarely goes publicly, because I think it is the most important part of the story. Why are scientists terrified to say this out loud? I have used that phrase deliberately because I think it captures something real about the sociology of physics at this particular moment. The word terrified is too strong, perhaps. Reluctant is more accurate. Institutionally cautious. There is a culture in academic physics, in the way funding is allocated, careers are built, papers are refereed, conferences are organized, that strongly rewards working within established frameworks and strongly penalizes departing from them. A junior physicist who stands up at a conference and says that she thinks the standard model and lambda CDM are fundamentally broken is not going to have an easy career. The reaction will not be excitement. It will be a request for a specific, testable, quantitative alternative. And if she does not have one, the polite consensus will be that she is getting ahead of the data. That consensus is not wrong exactly. Science requires rigor. The fact that anomalies exist does not justify abandoning well-tested frameworks. The history of physics is full of anomalies that turned out to be experimental errors or calculational mistakes. The conservative approach, keep working within the framework until the data force you out of it, is a reasonable methodological stance. But here is the problem. The anomalies are not resolving. The Hubble tension has gotten worse as the measurements have gotten better. The muon anomaly has persisted across multiple experimental runs. The S8 tension is robust across multiple independent measurements of large-scale structure. When anomalies compound across independent experimental domains, the conservative explanation that it is all noise becomes progressively less tenable. And yet the institutional response has not shifted proportionally. There is still a strong preference for explaining the anomalies away rather than confronting the possibility that the framework needs revision. Part of this is psychological. The frameworks we are talking about, quantum mechanics, the Standard Model, general relativity, were built by some of the greatest minds in human history. They have passed every experimental test they have been subjected to. They form the foundation of our entire technological civilization, from transistors to GPS to medical imaging. The idea that they are incomplete feels almost sacrilegious. Not because physicists are sentimental about their theories, but because incomplete in what way is such an enormously open and intimidating question, and part of it is practical. Revising a fundamental physical theory is not a small project. It is the work of decades, requiring the contributions of hundreds or thousands of researchers, enormous computational resources, and experimental programs that cost billions of dollars. You do not start that project on the basis of a few stubborn anomalies. You wait until the case is overwhelming. The question that is quietly burning in the corridors is whether the case is becoming overwhelming now. Let me tell you about a conversation I had some years ago with a colleague whose work I respect enormously. We were discussing the Hubble tension, which at that point was younger and smaller than it is now. And I asked him what he thought the most likely explanation was. He was quiet for a moment, the kind of quiet that in my experience means someone is deciding how honest to be, and then he said something that I have thought about many times since. He said, "I do not know, and I am not sure I want to know, because I am afraid that whatever the answer is, it is going to require rebuilding things I have spent my career on." That sentence, I think, captures the situation more honestly than most of the academic papers written about these anomalies. There is genuine fear, not of being wrong, physicists are trained to be wrong, but of the scale of the reconstruction that being wrong might require. Now let me tell you what I actually think might be happening. And I want to be clear that what I am about to say is personal scientific opinion, informed by years of thinking about these problems, but not a consensus view. It is my honest assessment of where the fingerprints are pointing. I think the anomalies we are seeing are connected. I do not think it is a coincidence that the Hubble tension, the S8 tension, and the muon anomaly are all appearing simultaneously. I think they may all be manifestations of the same underlying incompleteness in our theoretical framework. And I think that incompleteness is related to the boundary between quantum mechanics and gravity, the border between our two great theories of nature that we have never successfully reconciled. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes everything else as fields and particles operating in space-time. The two theories are extraordinarily successful in their respective domains, but they are fundamentally incompatible. They use different mathematical structures, different conceptual frameworks, different notions of what is real. When you try to apply both simultaneously, in the extreme conditions near black hole singularities or in the first moments after the Big Bang, the equations break down. They give infinities. They give nonsense. And we paper over those infinities with techniques called renormalization that work mathematically, but whose physical meaning remains obscure. My suspicion, and it is a suspicion informed by but not proven by the data, is that the boundary between gravity and quantum mechanics is not as sharp as we have assumed. That there is a regime at cosmological scales or at the scales of high-energy particle interactions where the two frameworks bleed into each other in ways we have not accounted for, where quantum effects on space-time, effects that we have assumed are negligible at large scales because they are presumably only important at the Planck length, actually accumulate and produce measurable deviations from what the classical theory predicts. If that is right, it would explain why the universe is expanding slightly faster than lambda CDM predicts. It would explain why matter is slightly less clumped than the model says it should be. And it would explain why the muon is behaving in a way that the standard model does not capture, because the standard model is built on quantum field theory and flat spacetime, and if spacetime is not exactly flat, not exactly smooth, if it has a quantum texture that we have been ignoring, then the predictions of the standard model would be subtly wrong. I am not the only one who has thought along these lines. There are researchers working on what are called quantum gravity corrections to cosmology, trying to calculate whether Planck scale physics can leave detectable signatures on cosmological observables. The calculations are difficult and the results are preliminary. But the program is serious and the people doing it are not cranks. They are working at the frontier of what is currently mathematically tractable. What would it take to confirm this? What would the smoking gun look like? There are several possibilities. One is a more precise measurement of the Hubble constant that makes the tension even sharper and rules out all conventional explanations. Several experiments are currently working toward this, including the DESI survey, which is measuring the three-dimensional distribution of millions of galaxies, and the Simons Observatory, which will measure the cosmic microwave background with unprecedented precision. If the tension survives and deepens, the pressure for a new theoretical framework will become very difficult to resist. Another possibility is a detection at the Large Hadron Collider, or its successor, the Future Circular Collider, which would be 3 times more powerful of a particle or interaction that does not fit the standard model. The muon anomaly predicts that something beyond the standard model must exist. If we can find it directly, we will have a new building block to work with, a new piece of the puzzle that might illuminate the broader picture. A third possibility, and this one I find particularly exciting, is a gravitational wave signal that encodes information about the quantum structure of space-time. Gravitational wave astronomy is new. We have been detecting these signals for less than a decade. The detector network is still in its early generations. As it becomes more sensitive, we will begin to hear not just the gravitational waves from merging black holes, but potentially subtler signals from the very fabric of space-time itself. Signatures of quantum gravity, of the granular structure of space at the Planck scale, might be encoded in the high-frequency noise of gravitational wave data in ways we have not yet learned to read. But I want to be honest about the timeline. These experiments will take years to decades. The theoretical work required to interpret what they find will take additional years. The kind of revolution I am describing, if it happens, will not happen quickly. Revolutions in physics never do. Copernicus died before his model was accepted. Newton built on Galileo and Kepler, who built on Copernicus, a chain of thought spanning a century. Einstein's 1,905 papers took decades to be fully absorbed into the culture of physics. The revolution in quantum mechanics, from Planck's 1,900 paper to the complete formulation of quantum field theory, took 50 years. The revolution, if there is one, that reconciles quantum mechanics and gravity and resolves the tensions we are currently observing will probably also take decades. We may be, right now, in the position of Planck in 1900, aware that something is wrong, able to measure the anomaly, unable to yet understand what it means. And here is what I find most interesting about that comparison. Planck introduced the quantum of action to resolve an anomaly called the ultraviolet catastrophe, a failure of classical physics to correctly predict the spectrum of blackbody radiation. He introduced it reluctantly, describing the quantum hypothesis as an act of desperation, as a purely formal assumption with no physical meaning. He thought it was a mathematical trick. He did not know that he was standing at the beginning of the most productive revolution in the history of science. I wonder sometimes whether the Hubble tension, the muon anomaly, the excess Bell violations are our ultraviolet catastrophe. Whether the theorist who resolves them will introduce some new conceptual element as reluctantly as Planck introduced the quantum, describing it as a formal trick, not yet understanding that it opens a door to an entirely new floor of physical reality. That is the thing about the laws of physics. They are not laws in the sense of legislation passed by some authority and enforceable by some power. They are our best current description of regularities in nature. And nature, as it has demonstrated with magnificent consistency throughout the history of science, always knows more than we do. It always has another layer. It always has another surprise. The laws of physics have been rewritten before. They were rewritten when Newton unified terrestrial and celestial mechanics. They were rewritten when Maxwell unified electricity and magnetism. They were rewritten when Einstein showed that space and time were not separate and absolute. They were rewritten when Bohr and Heisenberg and Schrödinger revealed the quantum world. And each time they were rewritten, the previous version was not thrown away. It was absorbed into something larger, something more complete, something that reduced to the old equations in the regime where the old equations worked, but that revealed new structure, new connections, new depths in the regime where the old equations failed. Whatever is rewriting the laws of physics now will do the same thing. Quantum mechanics will survive. General relativity will survive. The Standard Model will survive. They will be revealed to be excellent approximations to something deeper, valid descriptions of a limited domain. The way Newtonian mechanics is an excellent approximation to special relativity when velocities are small compared to the speed of light. But the something deeper will change things. It will change what we think space is, and time is, and matter is. It will connect things we currently think are separate. It will reveal that the universe is structured in a way we have not yet imagined. And it will raise new questions, deeper questions, questions we cannot currently formulate because we do not yet have the conceptual vocabulary to ask them. I find that genuinely exciting. Not despite the discomfort of not knowing, but partly because of it. The not knowing is the shape of the frontier. It is the feeling you get when you are standing at the edge of what has been understood and looking out at what has not. That feeling is not comfortable, but it is the most honest relationship you can have with a universe that does not owe you the comfort of a complete explanation. The scientists who are reluctant to say these things out loud are not wrong to be careful. Science demands care. It demands that you distinguish between what the data shows and what you suspect. It demands that you hold your interpretations loosely and your measurements tightly. But care can shade into silence. And silence about genuine anomalies is not a scientific virtue. It is a failure of nerve. The anomalies are real. They are growing. They are connected. And whatever they are telling us is important enough that the conversation needs to happen louder, more publicly, with less institutional anxiety about where it might lead. Because where it might lead is somewhere remarkable. It might lead to an understanding of the universe that makes the extraordinary physics of the 20th century look like a first draft. It might lead to a description of nature so complete and so deep that the questions we are currently struggling with, questions about dark matter and dark energy and the quantum structure of space-time, will seem as naive as the question of why the sun moves across the sky. The laws of physics are being rewritten. We do not know by whom or toward what final form, but the rewriting is happening. The fingerprints are there in the data for anyone willing to look honestly at them and say, without flinching, that they do not fit what we expected. That is not a crisis. It is an invitation. The universe is telling us it is stranger than our current story allows. And in my experience, the universe has never been wrong about that. If any of this has landed somewhere real for you, if it has shifted something in the way you think about what physics is and where it stands, I want to hear about it in the comments below. Tell me which anomaly surprised you most. Tell me where you think the next revolution is hiding. These conversations matter to me, and they matter to the broader project of keeping science honest and ambitious and open to surprise. And if you want more of this, the real physics, the genuine uncertainty, nothing smoothed over, subscribe. We go slowly here because some of the most important questions deserve it.